Machine learning is a balancing act. If we use standard linear regression on this data, we get a straight line. It's stable, but it's too rigid. It misses the curve completely. This is underfitting. So, we upgrade to polynomial regression. We give the model the freedom to bend. It fits the curve beautifully. But what happens if we give the model too much freedom? If we increase the degree of the polynomial? What if we let it do whatever it wants to minimize the error? We get this a chaotic oscillating mess. The model on the left has memorized the data. The model on the right has learned the actual pattern. How is this possible? How do we force a complex model to choose simplicity over chaos? The answer is regularization. Welcome to Decoding Complexities. I am Pradeep. Up until now, our model had only one goal: to minimize the error. It would do anything to drive that error to zero, including inflating its weights to massive numbers to create those wild loops. To fix this, we change the rules. We give the model a new goal. We say, I want you to minimize the error, but you will pay a penalty for the size of your weights. We control this penalty with a parameter usually called lambda. If lambda is 0, that means there is no penalty and no regularization is applied. If lambda is too high, the penalty is severe and forces the model to be simple. And the magic happens somewhere in between. There are two different methods for applying regularization. The first method is ridge regression. We penalize the squared value of the weights. Now, let's look at the calculus. When we take the derivative of this new loss function to find the minimum, something interesting happens. The derivative of the error gives us our standard normal equation. But the derivative of the penalty, which is the derivative of w square, gives us 2 lambda w. When we set this to 0 and solve for w, this extra term doesn't disappear. It gets absorbed into the matrix. It turns into lambda times the identity matrix. This means to solve ridge regression, we simply add lambda to the diagonal of our matrix before we invert it. This makes the matrix invertible and stable. But does it actually work? Let's plot this manual calculation against our data. Look at that. The wild oscillations are gone. By simply adding a number to the diagonal, we turn chaos into a smooth curve. We don't always implement this from scratch in production. Let's verify this using Scikit-Learn. Does the industry standard library gives us the same result? We fit the model and plot it right on top of our manual curve. It matches almost perfectly. This proves that Scikit-Learn isn't magic. It's just running the exact same linear algebra we just derived. But there is another method, Lasso regression. Here, we penalize the absolute value of the weights instead of the squared values we did for the ridge regression. Because of the sharp geometry of the absolute value, Lasso has a unique superpower. It can force the weights to become exactly 0. However, because the absolute value function has a sharp corner at 0, we cannot take a simple derivative like we did with the ridge regression. There is no simple matrix formula. So, we rely on Scikit-Learn's iterative solver for now. Look at the weights. We have most of zeros. Lasso looked at our 30 polynomial features, realized most were unnecessary and deleted them. It simplified our equation automatically. Let's visualize the Lasso curve. It creates a simple, robust model by selecting only the most important features. Now, let's see the full picture. Let's put everything on one graph. The red line minimizes the error but fails to learn. The green and purple lines accept a little bit of error to gain a massive amount of stability. This is the trade-off. We pay a penalty in training accuracy to gain performance on the new data. So, we started with a model that memorized the data. We used the tool of regularization to constrain it. and discovered that we can mathematically control the bias variance trade-off. We have mastered how to select features and stabilize our models. But what if the true pattern of the data isn't the features we selected at all? What if the secret structure is hidden inside the matrix itself, along the axis we haven't found yet? That's where eigenvectors come in, and that's what we will decode in the next video. If this deep dive was valuable, check out the detailed companion blog post and the Google Colab notebook linked in the description to run this code for yourself. Hit that like button and subscribe as we continue to decode the complexities of machine learning. Thank you for watching, and I will see you in the next one.